So continuing along the exponential function path, today specifically exponential modeling. And so looking specifically at the idea of growth and decay. So there's a couple different forms we could look at this equation in, but when we talk up here, exponential population model, one of the forms that we can talk about is right here, and that is if a population P is changing at a constant percentage rate, R, each year, then P of T equals what I call it P naught, P sub 0, I'm trying to think what you guys use, times 1 plus R to the power of T. Now, right here, where P naught is the initial population. So it's the population at time 0 is what that P sub 0 is. R up above was always listed as the percentage rate, and R is expressed as a decimal, as a percent usually is in an equation form. We express it as a decimal, and T, of course, is time. Okay. Now, growth versus decay. I mentioned yesterday real briefly at the end that our graphs that were increasing to the right were examples of growth, right? Our graphs that were decreasing to the right were examples of decay. Well, here's what we know. If our R value is bigger than 0, okay? In other words, that's going to come down to if we are adding, then it is going to be an example of exponential growth, and 1 plus R is what is known as the growth factor, okay? On the flip side of that, if R is less than 0, then we're going to be looking at a exponential decay situation. And your 1 plus R, which that would put R as a negative here, is the decay factor. Okay? So we're going to be talking a little bit about growth and decay and what we can do with those. And so example 1. In each of these, tell whether the population model is an exponential growth function or exponential decay function, and find the constant percentage rate of growth or decay. So I want to know growth or decay, and then I want the percentage rate of growth or decay. Okay. Thoughts on A?
Growth.
Why?
Because it's greater than 1.
Okay. When he says it's greater than 1, I'm kind of going with he's looking at that value there is greater than 1. And I agree, that is one way to tell that right there, because I see that's a 1 point something, that is one way to tell me it's growth. Now, I want to rewrite this in the form of this original equation up here. So if I rewrite this, 782,248, and I'm doing this just because we need to be able to identify R. Right now, we don't have R. But if we look at this original function, in raised to the power of T is 1 plus R. How could I rewrite this? This is going to be 1 plus what?
0.
Okay. 0.0135 raised to the T. Right there is your other way you know it's growth, because it's 1 plus the value. Okay, that's the other way we know it's growth. So, a couple of different reasons, but it is definitely growth. I need to know R. That's the decimal form. So, this does represent R right there. That's the decimal form. What about if I want it as the percentage rate form? Move the decimal over 2 points, and it is 1.35%. Change colors mid-problem. Oh, well. Okay, so there's an example of a population model. It's growth. We know it's growth because that value raised to the exponent was 1 point something. And then when we separate it out, it was 1 plus the r value. And so there's the idea when it said if r is greater than 0, it is growth. There's the idea it's a positive r value. Okay? Okay, B. What do you recognize on B? Okay, why are we saying decay?
Because it's
Okay, this number right here, it starts off with 0, doesn't it? Since it starts off with 0, I automatically know, whoops, I automatically know that it's a decay. Okay, now, with that in mind, we need to rewrite this because I need to know my r value. And this one's a little trickier. So if I rewrite this, the 1,203,368 stays the same. In your parentheses is always supposed to be the 1 plus r. Well, there's the 1. What am I looking for this time?
1 minus 0.985.
I agree it's going to be subtract.
Will it be
You do
0,
1
2?
minus that, and it would be 0.0.
If we want this, what's in my parentheses, to be equivalent, 1 minus 0.9858 is not equal to 0.9858. Does that make sense? So I need what I'm putting in this parentheses to equal 0.9858. So if you take your calculator and you figure out what 1 minus 0.9858 is, that's going to give you that 0.0142. So it's a little bit trickier on decay, but do we see that? Another reason we know it's decay, it was 0 out front, and what did I have to use in the middle here? We had to use a minus. Okay, that takes us back to if r is less than 0, then it is decay. Okay, so this is a decay problem. What is your percentage rate?
Negative 1.42%.
Okay, except we don't have to give it as a negative. Because we're stating it's a decay, we know that it is going down. So 1.42%. Okay. I guess I never labeled it here, but this is your R value. You've probably done something a little bit like this before, so it's probably not too brand new. Okay, example 2. Determine the exponential function with initial value equal 12, increasing at a rate of 8% per year. So my job is to, it says determine the exponential function. I want to write a function. Okay. What form were we given for today? P of t equals P naught times 1 plus r raised to the value of t. Okay. Our job is to create an equation that we could use to work problems in this scenario. What do you know?
12 and then in parentheses 1 plus 0.08.
Okay. Initial value of 12, that's going to go in for P naught. Increases at a rate of 8%. Well, what do we know about 8%? As a decimal, that is 0.08. So R is going to go as 0.08. And what's the other key word that you had to catch here? It's increasing. So if it's increasing, what's that mean? It's growth. You're going to be adding, yes? That could have just as easily said decreasing. Then you'd know it would have to be decay and subtracting. Fair enough? So if I write this out, P of t equals 12 times 1 plus 0.08 raised to the power of t. Obviously, if you didn't already, can you clean up that 1 plus 0.08? Some of you probably did that from the beginning, and that's fine. Okay, so as a final answer, if I'm writing this, one option would be P of t equals 12 times 1.08 raised to the power of t. And the idea here is this is a function that can find the population at a given time. In other words, you plug in the time, you can find the given population. Now, I will say I have an or written in my notes. And that or is just because I think in the lesson, in the homework, they sometimes bounce back and forth. This basic function was given in terms of P and T, yes? Do we always work in P and T? No, this specifically refers to population and time. You will also sometimes see it in terms of X and Y. And so you could just as easily have this equation as f of X or Y equals 12 times 1.08 raised to the power of X. And I would not count that wrong. Okay, so whether you put it in terms of P and T, or X and Y, or in this case, X and f of X, that would be fine too. Because I could also rewrite this as Y equals. So I just want you to be aware if you see X's and Y's, that's fine as well. Okay? Questions there? Okay. Well, let's go down and, I don't know, exponential functions definitely speak science. So let's go down and speak some science. Suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 350,000. Okay? Now, we're going to kind of tweak our equation from above, essentially. Okay? And I'll kind of show you different ways to get there. But eventually, notice it does say solving graphically. So eventually we are going to have to, because here's the deal. It's asking about a really big number, isn't it? 350,000. That's not a number that I just want to sit here and keep doubling. Okay? I want an option of how we can get there. So, and I want a little bit more specific than what that would give me. So let's think about, okay, what is our, how often do we double? Every hour, yes? So, I'm going to break this into pieces because I'm leading you somewhere. But what happens after 1 hour? 100 goes to 200, yes? And that is, I'm going to break this into pieces, just bear with me. That is because 100 times 2, right? You take the 100, you're doubling it, it's times 2. Now, I'm also going to write that as 100 times 2 to the first. And you'll see why. But yes, eventually it ends up at 200. Okay? So, what do you know after 2 hours? Okay, we were at 200. We're now at 400, yes? Now, if I break this down into the pieces, though, what was it? It was the original 100 times 2 the first hour and times 2 the second hour. How can I rewrite that? That is 100 times 2 to the second. You see where I'm going with this, right? One more, then we'll write our equation. What about after 3 hours? Okay, 400 will double to 800. How do we get to 800? It was the original 100 times 2 the first hour, times 2 the second hour, and times 2 to the third hour, which is rewritten as 100 times 2 to the third. Okay? May seem kind of basic, but it gets me to where I want to be. Because what I want you to be able to do, can you write an equation now? Yeah. P of t is going to be equal to what? What were we doing every time?
100.
100 times what?
Oh, times 2.
Times 2 to
T.
the t power, yes? Do you see how that flows? Every time it was 100, and each time we kept adding a 2, right? So this is, and I know it didn't actually ask me to write an equation for this, but this is one of the ways we can do this, okay? Because it does suggest that we solve this graphically. Now, what do you think this 2 represents here? That 2 represents the fact that what are we doing in this problem? We're doubling, okay? If you think up to my original problem was 1 plus r. Well, what is my r here?
2.
If you're doubling it, you are increasing by, well, times 2, but what kind of percent is that? You're increasing by, you're taking what you had, and you add itself to it,
100%.
you're increasing by 100%. So the idea that this 2 plus 2 is really 1 plus 1, if you will. Okay, that's where the doubling comes from. Now, in all honesty, it's just easy to shortcut and say, oh, that's going to be a 2, isn't it? It's doubling, it's going to be a base of 2. But that's why it happens like that. Okay. Now, we want to know when what is happening?
When it gets to T.
When 350,000. Okay, now, so essentially we want to know when this equation equals 350,000. But here's the deal. Do we have ways to solve that yet? Not yet. That's 3.5, 3.4, 3.5, something like that. Okay? We will have ways to solve that eventually. We're not there yet. Okay? This is where we're going to look at graphing. Because we want to know, when does this equation equal what? 350,000. So what we're going to do is we're going to graph both of these as equations. We're going to graph P of t equals 100 times 2 to the t, and we're going to graph P of t equals 350,000. The idea is I want to know, when do these equations equal each other? And so what am I going to be looking for on my graph? If the equations equal each other, that's going to be when the equations cross, when they intersect. Okay? So we're going to be looking at when they intersect. Okay? I'll sketch a graph here in a moment. So we're going to type it in because we're going to have to do a little finagling. I'll tell you up front, we're going to have to do a little finagling. Because 350,000, is that something we normally graph? Exactly, you're not going to see it, are you? So 100 times 2 to the x, 350,000. Okay, I'm going to start myself off on just a Zoom 6, standard Zoom screen. Well, you see the exponential function, yes? And here's what I will tell you. Is it going to cross the x-axis eventually? It is. Remember we talked about these graphs? They're exponential functions. It's going something like that. It's just going up really steep. But we can't see 350,000, can we? So, we need to do some finagling. I don't think I would recommend just zooming out. That's not going to really work for you. Okay, I would change the window by hand. I don't know, if you zoomed out enough, maybe you could then zoom back in, but it takes a little bit to get 350,000. Okay. What needs to change here on my window? If we want to be able to see 350,000, 350,000 is what kind of value? Is that x or y?
X.
Y.
It's a y value.
Yeah.
Okay, so I'm going to go change my y min and y max. Do I need to have my y min way down at -10? No. My x max has to be bigger than, or my y max, excuse me, has to be bigger than 350,000. Okay, so I would narrow this down. So let's see, below 350,000. You could do like 349,000, but you're still 1,000 away. I don't remember what I've used in the past. So if we do 349,000, did you say 900?
Yeah.
Or do you, 349,900. That's still 100 below, isn't it? But then equivalent above would be 350,100. Okay. And knowing what I know, we're still going to have to do a little tweaking, but let's see what that gives us.
Oh.
It does. You have to give it a moment. It was still graphing. So that line, and if you go back and look, that red line is my 350,000. So it gives me the horizontal line. What it doesn't give me is my exponential curve. Now, that has to do with my exponential curve just does not happen to be between -10 and +10 at this moment in time. Okay? So I'm going to go back to my window. What can I definitely get rid of here? Do I need negatives?
No.
No. We're not going to have it. It's not going to happen in negative time. X max, well, it already wasn't showing at 10, so we need to go bigger, don't we? Now, I'll be honest, you don't have to go a whole lot bigger. I do something like a 15 or a 20. My normal brain would probably go 20. I also know where the answer is, so I'm saying you could go 15. Now, because we're zoomed in, I know that blue line. Look, blue, blue. That's my exponential graph. It just looks like a straight line right there because of where we're zoomed in. Okay? Okay. What do we want to know? Where these two lines intersect. Have we used intersect in here before? It's in a menu that we use all the time. Go to your calc menu, which is the second and the trace button. Yes? Notice, what do you have on the calc menu? Number 5 is intersect. Okay? So hit intersect. Now, it asks you questions. First curve. This is just saying, do you want y1 to be your first curve? Yes, that's one of the two curves I'm looking at, right? I only have these two curves in. Hit enter. Second curve. It's saying, do you want y2 to be your second curve? Yes. Hit enter. A guess. A guess just means, and honestly the guess doesn't matter in this case because we haven't zoomed in so much, but take your cursor to where the intersection point is and hit enter. Notice now it's telling me intersection. So it's saying, yes, these intersect. By the way, that was second calc. Intersect is what we did on the calculator there. You need to write yourself a note. And we found, oh, I forgot to write in. We found that point right there, didn't we? What's the answer I need?
X equals 11.
Yeah. And I do have it to just 2 decimal places on my answer key, I believe. Yeah. So intersects at, I'm going to say T officially, 11.77. What was T in terms of? This is in terms of hours. Okay. Now, could you have kept going? It wouldn't have taken too long before you got to 350,000 doing this by hand, right? It would have only taken you 12 times, but we wouldn't have been able to get to the specific 11.77, or the fact that it's about 11 3/4 hours. Okay? So, questions there. And hopefully you see why this time it was important to write an equation, because I can't graph it without having an equation. Okay? Okay. That was our situation where our culture was doubling every hour. So if we just doubled, guess what? Now we get to?
Triple.
No. Half-life. This is what? Chemistry? Yes? No? Or is it in biology? Chemistry. Okay. So, now, instead of doubling, we're going to talk about the half-life. Suppose the half-life of a certain radioactive substance is 20 days, and there are 4 grams present initially. Find the time when there will be 1 gram of the substance remaining. And little definition there, half time is the time it takes for a substance to decay itself to half of the original amount. In case that wasn't obvious. Okay. What's our time interval we're talking about here? Days. Specifically, how often do we want to talk? 20 days. Okay, so last time I could just do 1 hour, 2 hours, 3 hours. This time I'm going to talk days, but I need to talk increments of 20 days. So, what do you notice after 20 days? Well, initially there are 4 grams.
So if we look at half, it would be 2.
Okay, 4 multiplied by a half, which I'm going to write this out kind of like I did last time. It's 4 times half to the first, and that is going to be 2 grams. Yes? Okay. What's the next increment of time we would want to look at?
40 days?
40 days, right? Because we're going to increments of 20. So if you take another 20, now we're looking at 40 days. Well, what do you know at 40 days? Well, we had 2, and now we're going to be down to 1. And that's because what? We had the original 4. We halved it at 20 minutes, and then what happened? Or 20 days, excuse me. And then we halved it again at 40 days. So here we're looking at 4 times 1/2 to the second. Now, in all honesty, what did we just find? The answer. Okay, this one was a easier one, but I do want to talk about writing the equations because you have some equations to write in homework. So, find the time when there'll be 1 gram of the substance remaining. Well, that's going to be after 40 days. That is your official answer. Not going to try and hide that or cover it or anything. That's true. Now, think about what would be the equation we would write here, because there is a little trick. And again, I know they don't have us write an equation here, but P of T equals 4, and then 1/2. Now, I'm not going to put T though. This is where our trick is. But you see why the 4 is there, right? That was our initial amount, just like 100 was our initial amount here. Why is this a 1/2?
Because you're dividing.
Yeah, this is because this time it is half-life, right? Last time it was doubling, but because it's half-life, it's a 1/2. You can also think of this, if you're taking half of something, you're taking away 50%. So you can think of it as 1 minus 0.5, if that works for you. Okay. Now, what's the catch? We did 1/2 to the first and 1/2 to the second, but is that the value we would really plug in? Did we talk after 1 of something? It was 1 increment, but what was that increment? 20 days. This was 40 days. How can I plug in 20 and 40 and get them to be 1 and 2? And doing the same thing to both. Divide them by 20. Are you seeing that? So when I go to put my power here, my power is going to be T, but divided by 20. Does that make sense? And that comes down to, on the previous example, it was after 1 hour, 2 hours, 3 hours. On this example, it wasn't after 1 day, 2 days, 3 days. Each increment was 20 days. So you have to divide, if you're going to plug in 20 and 40, you have to divide by 20. Okay, so that would be the equation. Again, I know they didn't ask for equation, but you have some equations in homework. Okay. So not I remember what I remember the timing of this lesson today, but I'll take it. Page 264, 1 through 18 is what you have to do tomorrow.